Good evening, everybody. Thank you for the opportunity to have a little chat with you. So, a little bit about me. I sort of get around for a while. I've been 40 years or something in electronics, in all sorts of things, but always sort of in new product development. Most of them in electronics or some form of firmware or software related to that electronics. So that's really, over the years I've done many things, but that's really the thing that I discovered I really like myself is that I'm an engineer. I like to do things and I like to invent things. So, and over the years it's been many things. Anything from, before GPS actually existed, I was actually developing a GPS receiver processor board already for the first experimental GPS satellites that was there. So that's how far back it goes. Encryption devices, radio communication systems, feral animal control devices, and I can probably have stories about those. It's just tonight I'm talking about some stuff around micro-X, which is X-ray, which is where I currently work, in which I'm playing a technical lead role for a new product development, and we're going to get into some details on some of the stuff. And essentially technical lead and system architect, because I'm trying to pull everything together to make it all work. So just quickly, what is micro-X? Micro-X is a company down here in Adelaide, and one of the unique things that micro-X is doing is that we invented a new way of actually producing X-rays, different from classical systems, and we're currently the only one in the world that actually can do that on a production level. Lots of people are actually experimenting with. We're the only one that actually have a product in something we call cold cathode X-ray tubes, and we'll get into some of that a bit on. So, and we're down in Tonsley. So that's all innovation district. So when you're coming down to Tonsley, we're right next to the Flinders Uni building, and really when we originally started, we were still a very young company. We only sort of existed for 6-7 years altogether, and when we originally invented this, we actually needed to have manufacturing people, and we actually started pulling in people from the auto industry that actually was winding up. So we actually have a lot of assembly staff that actually used to be ex-Holland people. So that's where we come from. And very quickly, and that's one of the things that I really enjoyed when I actually joined micro-X, is that we're not just a startup that actually has high risk and possibly no rewards. No, micro-X actually has a product. So we developed, with help from external contractors and consultants, we developed a little cart you actually can wheel around airports, or not airports, hospitals, to actually take X-rays at the bedside of a patient. And so we're actually manufacturing it and we're selling it all over the world. So that actually provides part of our income and also our stability base on what we're doing. But the core of this technology is this cold cathode technology, in which we're really currently the only one in the world. And part of the aim of the company is that we're trying to use this technology to develop new products that are unique, because we actually can capitalize on the unique features, being really small and doesn't produce a lot of heat, of X-ray production. So one of the things we're working, and the one I'm working on, and we're going to talk a little bit more tonight, is the miniature baggage scanner, which is this one, which is aimed for security scanning in airports, and actually changing the whole concept of baggage scanning in airports around, and actually making it into more of a self-service solution, as opposed to lots of people that actually stand and sort of usher you through the lanes and actually put everything on the conveyor belt and people looking at screens. We're actually part of a process of actually that's going to automate that and actually becomes more self-service. In the same way as you actually get check-ins on airports, where you no longer actually talk to a person, but you actually swipe your scanner thing on your phone and then you're checked in. And that's what we're aiming for. Another one we're aiming for is the product that we're seeing on the left. That actually is it's a special type of X-ray equipment. It's backscatter X-ray, and it's like not normally X-rays are about transmission, so you shine X-ray through something and you take a picture at the back. This product actually looks at the reflection of X-ray that come back, which means particularly for military or security applications where you try to do scanning of a bomb or something, or like you see a bag and it's leaning against the wall and you really don't want to touch it because you don't know what's in there, you can't really put an X-ray film behind it. So this will actually, you can stand it in front of it and it will actually scan in 3 dimensions what this contents of this bag is. It's a bit more fuzzy than what you typically see in a transmission style X-ray, but at the same time it gives you a lot of information because you can identify phones and electronics and wires and batteries and all that sort of things. Anything that may be suspicious, you can identify on it. So that's another style of things. And so that middle one is the one that we sort of as the highest priority right at the moment, what we're aiming for. It's closest to actually getting the product. This second magnetic scanner is the second one. And the third one is, that is a mock-up model, what you're there seeing. But what you're seeing there is a piece of X-ray equipment which is able to produce a CT scan of somebody's head. And this is aimed for treating stroke patients. So stroke patients, they talk about with stroke patients the golden hour, meaning like you need to know what is happening inside the head of that person that just had the stroke to work out what sort of medication you can give him. That needs to happen within the first hour, and therefore a CT scan is critical to saving that person. That piece of equipment is the normal CT scans that you see in airports or also in hospitals have X-ray equipment, which is a massive thing, and it's this massive equipment, and there's an X-ray tube turning around like this over rails. That one uses 32 miniature X-ray tubes, no moving parts, and we can actually take a CT scan of somebody's head, and the whole equipment is small and light enough to fit in every ambulance. The only solution we currently have in Australia is in Melbourne, where they actually have 2 trucks that actually run around with CT equipment in it. But half the time they're not available, and this solution would give you an opportunity to put one in every ambulance or even in a Royal Flying Doctor's aircraft, because of the weight and the power requirements are so small relative to all the existing equipment. So that's very exciting, but that actually isn't a really, you talk about research and development, that's a really big R still, and we have still many challenges to go for, but that's what we're working on. So, just to get into the mood of what we're talking about, and just have a little chat about what actually are X-rays, right? So, X-rays are some sort of electromagnetic waves, same sort of thing as light or the radio waves from your phone, but they sit in a different spectrum, okay? And they sit way more in the spectrum over there. So this visual spectrum, this is the light that we see. So this is the, what do you call it? The rainbows that we actually can see. And this is where all the radio stuff is. And then more, it's actually you get into X-rays and eventually gamma rays, which is all part of radiation and what do you call it? I forgot what I wanted to say now, but that's what X-ray is. But the key thing is, there are what we call photons. When we talk about X-ray, we actually talk about photons. Light is photons, X-rays are photons. It's just that X-ray photons are operating at a different energy level, and that energy level is so high, it allows you to pass, the photons pass through materials. But it also is such high energy, it can bounce onto something and actually can knock off an electron out of the atom, which means that the atom chemically changes. That is actually why X-ray needs to be regulated, because it can actually be damaging to tissue. And another thing to remember from X-rays actually is on the picture on the left. Is it left? No, you're right. Which is actually X-rays. When you talk about X-rays, everybody thinks, well, this is just X-rays, but no, it's not. X-rays actually have a spectrum, just like light has a spectrum where you actually have red light and blue light. X-rays have a spectrum too, that's determined by the energy level that's actually being used. And we play around with that. So a lot of the medical equipment typically have what is actually in this ping is an energy level of 100 kilovolts. But which is enough to actually get through soft tissues like body parts. But if you actually need to get through metals, you actually need to go much higher. So our baggage scanning equipment runs 160,000 volts. And there's X-ray equipment available to actually scan complete shipping containers all in one hit. That is a lot of metal actually to go through and a lot of material to actually get through. That sort of X-ray equipment runs on megavolts. So it's a factor higher yet again. Yes?
Is that dangerous to biological tissue if someone was to stand in front of that?
Sorry, I didn't get that.
Would that be dangerous to biological tissue if someone was to stand in front of that X-ray of such high energy? Would that be too dangerous?
Absolutely. I mean, and with X-ray, the golden rules is around X-ray when you're trying to talk about safety on X-ray is actually distance and duration and the intensity. So all those factors all come to in account. And sort of in very technical terms, we talk about a thing called mass, which is M-capital-A-S, which stands for the milliamps of current that actually goes through the X-ray tubes, times the times in S in seconds, and that actually gives a particular value. And that's what you find in regulations, that a person, for a hand, for an arm, you only need this amount of mass. For a hip, which is bigger, you need this amount of mass. And different energy levels, and there's some filtering that happens on the energy levels, whereby, because the one at the 40 where the big peak is, typically is not very useful, so they actually tend to filter that out and actually use some higher levels by putting different materials in front of the X-ray to stop it in the right way. So there's a lot going on there on that respect. But if we're now talking about this picture, in the end, what actually is happening with X-ray tubes is that you need a couple of things. One of them is you need to have some way of actually exciting your electrons to allow them to flow freely. And the classic way of doing that is actually by heating a filament, in the same way as you have the old hot glass, what's the right wording? Yeah. So they get hot, and because they get hot, the electrons actually get excited and they actually are willing to actually let go. And then the second thing you need is you need to have a high voltage. So between here and here, you need this high voltage somewhere starting from 40 kilovolts or higher in order to actually attract those electrons to fly away and actually hit in what we call the anode. And that typically is a very copper thing. I actually get some samples, like here. There's a big of copper block in here. That is just to handle the heat that's going on, because on top of that anode, there's a little sliver of metal, very dense metal, like tungsten is a very dense metal. And what happens is that the electrons bump into the tungsten, and then part of what's happening is that is where the X-ray is produced. The interesting thing is that X-ray is only about 1% of the amount of electrons that bump into it. So the rest, it all disappears in heat. And when you're talking about 160,000 volts and you do 7.5 milliamps, you're talking about a kilowatt. So that is all interesting stuff that you need to manage. So that is the pure principle of how X-ray tubes work. In Micro-X, we do it differently. We don't use a filament to heat things up. We actually use something else. And we're talking about cold cathode technology. And this gets maybe very technical, but it actually means is that if you actually get, you know, those lightning diverters that you put on buildings, essentially that's a very small spike. And that actually, when you use that, it actually attracts the electric field around it, so that actually the lightning actually hits that rod. That also works in reverse. In what we're doing is that if you have a very small spiky thing, and now we're talking in this thing, we're talking about micrometers, and you put some voltage on it, then all the electrons actually start to get into that little spike. And because of getting that little spike, they have almost nowhere to go other than to fly out. Very simply said, that's sort of the principle of it. And in a cold cathode technology, what we then actually have in that picture on your right is that there is a substrate, And that substrate is what we then use has nanoparticles in it, which is essentially a little bit of all these little spiky things that actually spike up, and we apply a voltage onto it, and that actually attracts those electrons out of those spiky points, out of those nanotubes that we actually have in there. And then they go through an item marked with C, which is we call the grid. And then once it hits that, it actually flies through, and then we actually accelerate the electrons all the way to the anode. So that's roughly the principle of a cold cathode tube. The beauty of this is that as opposed to a heated element, you can't turn on a heated element very quickly. I mean, you can turn it on and you see it glow up, and then when you turn it off, you see it glow down. I mean, it actually goes with that sort of speed that you visually see it. We can turn these things on in microseconds. So we can actually do really fast pulsing of X-rays, which you wouldn't otherwise be able to do. And that's a unique feature that we're actually trying to utilize in some of our products. Make sense? Everybody with me so far? Cool. So, in our system, so other than the little spiky one, we're actually using nanostructures, and these are some pictures of some of these nanostructures. I actually have one here with me. It's like this. This is the emitter. And when you put that on an electron microscope, it sort of looks like this, and it's sort of a bit like a sandpaper rough surface. Essentially, it has all these little nanoparticles that actually are pointing all directions. Some of them point up, and those are the ones that actually produce the electrons necessary for creating X-rays. Yes? So, comparing these things together, here we actually, so the classic one is an heating element, and there's an anode, and typically that sits in some sort of glass level container. That whole thing gets hot. It actually needs to be shielded. It needs to be, in order to actually make sure that the X-ray only comes out where you want to come out and not everywhere else. It actually gets hot. You need to cool it down. So typically what happens with X-ray tubes is you put this in a large container, you fill the whole thing with oil, and you use the oil to cool it, but then the whole container is actually a lead shielded box. Compared to our one, that doesn't get hot. So this is, as you see it, this is it. This is essentially, this is the full X-ray thing, complete. And we don't have to cool it anything further from there, which means the whole thing is a lot more compact. And when you're actually putting it into the classic, we're tenfold lighter than classic X-ray tubes. These are X-ray tubes of comparable capacity in terms of how much X-ray they can produce. Because you get small ones for dentistry, there's very small ones, and for CNT machines are really big ones. But these are comparable, and they are sort of like, the classic one is 29 kilos and we are at 2.3 kilos. So that's a sort of level comparison. And that makes a lot of difference, because in that one that we saw in the earlier pictures, the X-ray is actually in this head, which means we actually can move it up and down and we can point it anywhere we like. We're not stuck to some rigid frame where it actually needs to be mounted to carry that weight. You can actually move it with one hand. And in terms of usability, that makes a lot of difference.
With that situation there, what if the patient is, say, it's on a bed and not able to move, or something, it's just too painful for them to move? Are you able to go through the bed and have the X-ray go through the bed from the outside?
Yeah, that's correct. I mean, that product that we showed in some of the early slides is what we call our rover. That actually is designed for bedside use. And so because it's light enough, it actually operates on a battery. You can actually run it all day, take pictures all day, all on battery, and you can run it around on a hospital ward, and you actually can take bedside pictures. And that is a huge benefit, because anything equivalent to that is a lot heavier. And I heard stories where they actually had these things where they actually needed to be wheeled around hospital wards, but they had electric motors to move them because they were too heavy to push. And when you push them in the elevator says, whoa, oh, and it actually sinks 5 centimeters under the door pull because of the weight. So there's a lot of benefits of actually using this technology in this sort of way. But we're getting to more exciting stuff with this technology in some of the later things.
You've got nicely
They are patented, but I can freely talk about this because good luck reproducing this because it is actually the chemistry of how we produce this. That actually is the patent and that actually is the secret. That I don't have any access for. This is actually closely guarded. There's only like 2 or 3 people in the company that actually know what this is. So, but everything else is as public as we can have it. And we're quite happy to talk about it. But most of this is all on our website anyway. So from that perspective, there's no harm in there. So on that note, we're evolving the tube designs for different purposes. So this is the front in the front. It's the one that I showed you here on the table. This is what we call our nugget tube. I mean, we've come up with weird names for these things. And this is then the example of the X-ray tubes that we're actually currently developing, which is the one in the middle. This is what we use in the baggage scanning and also in the bomb detecting unit. And we call this one our Columbus tube. I don't know where that came from, but we call that the Columbus tube. This pipe is part of the process of actually getting the vacuum out of this tube. Because, I mean, even though this is open, obviously that's not supposed to be open. This is closely secured, welded close to actually to hold vacuum at a very tight level. And this actually is to pump it empty in terms of, and actually to get the tube to work. This is a critical part. In the end, when we do this, we actually punch this off and we actually cut this off. So that's part of the process. And the final one, the one we're currently working on, and this is only a 3D printed model, but this is roughly equivalent to the X-ray tube that we're developing for the CT scanner for ambulances. With the idea is that we would have 31 of these in a row, right next to each other. So there's no moving parts, we just electronically switch them on and off, one after the other, and in that way we can actually get a CT image happening in a 3D-dimensional image from a head of a person.
How does this top actually not allow the X-rays to escape out of it because it's metal, but where the other glass one you had to shield it to send the X-rays where you want them?
That's a very good question. There's a number of aspects to it. First of all, the stainless steel on the outside is actually helping to actually do it. The part of the anode it actually has stands on an angle, so we bounce the X-rays into a particular direction. And the other part of this is that there is some shielding around the tube. And this is not lead, this is a material, it looks a bit plasticky, but it's actually quite heavy. It's a material that we call EcoMass, and it's still injection molded, but it is a sort of a plastic that has really high density fibers in it, and it starts to work almost like lead in that sense. Lead is very dense, and that's why we use it for shielding. And we calculated and worked it out that all this tube needs is this. If you go from this one operates on 120 kilovolts, if you go to 160 kilovolts, 160 kilovolts penetrates better, which means this one would not be enough for the 160 kilovolts. And some of that, and currently, and we're sort of jumping forward a little bit, that baggage scanner thing, a significant portion of that weight of that unit is actually lead. To shield it all off, shield in the doors, shield in the panels. We open the door to actually get access to it, but when it closes, it becomes one enclosed lead box. And that's why the machine is actually like 700 kilos, which means you really need a forklift to move it around because it's actually too heavy to use in any other way. So that's the chapter on X-ray tubes. Another important part of what we've been doing is we actually develop, one of the things we're also developing is actually high voltage generators. So we're actually generating or building the power supplies to generate 120 kilovolts or 160 kilovolts. And then you get into an interesting realm of, okay, 160,000 volts. If you actually do that in air, that actually gets really nice sparks. So we need to insulate that, and we need to find ways of actually insulating that. And for the last few years we have been going and actually developing processes around potting them in epoxy to help with that insulation. But that's not an easy process in itself. So, because if you don't insulate proper, you get all these sort of effects, whereby then in the middle picture we had a 40 kilovolt arc just in air because we did something silly. So, and in some of these cases, and it's not necessarily always arcing, sometimes it actually just gets into the material and actually starts to creep, and when that arc is actually happening and some sort of current is flowing, it carbonizes and actually grows. And then you actually get these nice little trees like this, or something like this, where there's simply the electric field keeps on growing until it finally just breaks down completely and you're done. And on the other pictures we have some things where we actually previously we had potted as part of a generator to actually generate these high voltages, and then we were testing it, and then the whole thing just says poof. And then obviously we want to know where it actually said poof. So we break it open, so that's why it looks a bit coarse, but we have to find what the root cause of these things. And sometimes you get these little arcs where there's a little round little black dot, but there's actually a massive field of some of these tree growths underneath. So it's tricky stuff.
Marco, you obviously tried various silicons.
We're using several number of things, and I'll get to that in a sec if you hold on to that question. And it's not that long ago, because only in 2020 we really starting to getting into this potting game, and we were very pragmatic. I mean, we're just using little cups for muffins to mix stuff and actually create pottings for things. And one of the first tasks that we needed to do is actually find the right material that had the right dielectric strength and insulation capabilities of what we needed to do. So some of these first experimental things were we actually using molds, whereby we had copper blocks and we filled the cavity in between them with the material that we wanted to test, and we just went for it and actually blew it up, just to try to where it actually would blow up. And so there was a lot of experimenting going on there. So that was in 2021. That's only just before I started with MicroX, and sometimes I even didn't realize how close we were still with that sort of stuff. And lots of experimenting where we actually epoxied stuff inside and we're putting probes in, and epoxy is an exothermal process. So there's all sorts of funny things happening when the whole thing get mixed and actually then gets hot, and then what happens to the electronics that actually gets hot. And so there's a lot of questions that we actually have to go through. And there's more to this. Like, this is the list of resin we all tried. Okay? So I can't read it, you can't read it on the slide, but it's just showing an indication on how many things we actually tried and all the variations we did. So there's some transparent ones and some silicon ones and some glassy ones, and in the end the one at the bottom is called megapoxy, which apparently is a known recipe to some extent, but it's actually also specially formulated for us while we worked with this manufacturer of this epoxy on what the best one is. So we found one that actually was pretty good, and then we worked with them to change some of the properties in the epoxy to actually work out, can we actually make it better?
What's the typical use case for that brand of epoxy?
It is very often used in high voltage application already, like in transformers for electrical systems and things like that. It's just that the voltages that they operate with is not the level that we are operating at. So it's sort of out of bounds in terms of worthy things. And things like, they typically specify the dielectric strength on AC, 50 hertz or 60 hertz. We use DC, and we use it in a factor 10 more than what they typically use it at. So that's where the differences come in. So, and these first years, so from 2020 evolving to 2021, there's a lot of experimenting going on. It was really sort of agricultural. We were sort of like, it's sort of a backshed style operation in how we were doing things. And a lot of experimentation, and this is the first pass Because one of the things we're doing is actually we need to make sure that we actually extract any sort of air out of the epoxy. So there's a part A and a part B in the epoxy, and we actually rotate these things under vacuum and we pull it out. And even there, we had to learn how far we actually could go. Because at some point, we actually vacuumed it so hard, we actually start to boil. You know how you sort of sometimes see these experiments where you can put a cup of water in cold water under a vacuum pump and it starts to boil? We were boiling the part A and the B at some point. So we had to find the threshold point where it says, okay, well, this is how much we can do to actually extract the air out of it, but not to boil off the contents of the actual material itself, because suddenly you actually get an epoxy that no longer works. And there's all sort of funny things happening on that level, and I have some examples here on where things went wrong. The other thing, of course, is that at some point we really started getting into the high voltages and 120,000 volts, so we had to do a lot of safety style stuff whereby we put everything into basically Faraday cages to stop them from hurting people and actually make sure that things went safe. And we had special loads, we had special things. This is sort of like a dummy load. Like we typically when you're generating a power supply, you need something to test it with, right? So we had special dummy loads that actually can handle 120,000 volts. And some of these things require hoists. And here's another picture on that sort of thing, is that we talked about epoxy being exothermic. And when you actually have a massive blob of epoxy, it actually heats up from the inside in. And as part of the heating, it changes in the way it behaves. It actually shrinks more, and you get funny effects happening. And we didn't want any of that. So one of the things we're doing is that block that you see on the left there is one of our generators when we're first doing it. We're actually putting computer coolers onto the thing to keep it cool. So we actually can control the exothermic process of the epoxy to slow it down. Because we don't want it fast, we just want it right. So, and a lot of that, there's a lot of experimenting, a lot of stuff happening. And just on the basics then, is that, so we have a part A, we have a part B, there's some stirring going on slowly while we're actually extracting it extracting the air out of it. That takes a couple of hours, but even there, we had to go through the learnings on how long we do this. Because at some point we were convinced we can do it all weekend. And then eventually we get funny results in the end result on the potting where it actually didn't work as we felt it was, because we were steering it too much to the point where we actually start to break down the components inside the potting mix, so it no longer works. Because potting mix has like particles floating into a fluid, and then when you're stirring it too much, the particles eventually sink to the bottom and then no longer float, and then you actually get a ding of epoxy again. So all these learnings that we need to do, so we had to find out by the hard way. You can stir for 5 hours and that's it. You need to stop, otherwise you're screwing up your epoxy. Then after the vacuum A and B, under vacuum, we transfer the part B into part A, then we stir it again, all under vacuum, to mix it, and even there's a learning process on how well you can mix it. And then after we actually get the part A and the part B, we have, as you may know from epoxy, we have about half an hour to get this right. We have the box in another vacuum chamber, and we actually, by pulling the vacuum chamber, we control the flow, and we fill the material item from the bottom up to make sure that we don't trap any air bubbles into the thing while it actually is all happening. But if you do that too fast, you create air bubbles. But if you go too slow, the whole epoxy already starts to set before you're done. So there you actually get these funny results like this. So here we actually tried to pot something, and then the epoxy eventually didn't flow anymore, and we just had a boo-boo. And that problem goes up by the time the volume of epoxy you're doing. So here's another one, and we're finding there's all these things. So we created one of these items that we have here in plexiglass, so we actually can potentially see what's happening in how the epoxy flows in this thing. So this was all part of the experimenting that we were doing.
Sorry, Margaret. So you're moving mixed epoxy around through feed lines and stuff. Are they then sacrificial?
Yes. And it is even down to the point that in order to actually get the mix right, we were weighing off a part A and we're weighing off part B and we're mixing it by weight. And it was even to the point whereby we said, oh, we need 5 liters of potted mix. We still mixed the same quantity every time. Like we actually mixed enough for 10 liters, even though we used 5 and we threw the other one away. And then the buckets that were all in got thrown away and the feed lines get thrown away. So it was a very, very manual process, and I sort of show you a picture of something new that we recently, only this month, actually got working, that actually does it a lot better and actually has a lot less sacrificial stuff going on. But the principle of actually filling it from the bottom slowly with a given rate still applies. So this is a picture of only July last year what our potting setup was. So we actually had those chambers. They actually had stirrers sitting in the top. They were vacuum chambers, or they get vacuum pumped to a certain level and they stir the epoxy mix. Since that picture was taken, we actually put timers on the wall to say, well, no longer than 5 hours, or this mixing is no longer than 2.5 minutes, and actually to control the process, because we're really struggling of actually controlling the process. I mean, I thought I worked for an electronics company, but the amount of chemistry that goes on here is just phenomenal. So there's a lot of manual stuff happening, and it's only sort of recently we started to actually get into the habit of actually taking samples before we mix of the raw A material, the sample of the B material, weigh that it actually is the right consistency, mix it, measure it again, pot the whole thing, measure it again at the end, and actually compare these results whether we actually are at the right level. Because if you mix A and B, we have to come out at 0.15 something and actually make sure that we actually have the right mix. So there's a lot of stuff going on. And other than the potting, so now we're actually coming to a high voltage generator stuff, is that this is a product we developed from scratch. So here we actually developed some actual electronics from scratch, but it actually relies on this potting to work. And this generator is part of the medical equipment, so this runs up to 120 kilovolts. And it's quite a challenge, and then you feed the thing where we actually had this external hosing, this sacrificial hosing that sort of sits on the outside to actually make sure we fill it from the bottom and actually then fill it up towards the top. But in that generator again, we come through all these learning points of what are electric fields, and when you're actually talking about electric fields at these sort of levels, all sort of weird things happen. And then we find the hard way is that when you actually have something in there where you actually have a metal outside and you have some screws there, then the amount of intensity of the electric field that happens there, actually that becomes a failure point. So we were learning to avoid all these things and make sure that everything is shaped in the right way. It doesn't have any spiky corners or anything. Everything is rounded off, metal bits away from each other. And then you get these sort of little things where you're actually using it, and then you start seeing this growth of electric fields starting from the center, growing outwards and blowing things up.
How deep is that? Are they cuts?
Sorry?
Are they actual cuts, or are they just on the surface? How deep are they?
Well, what you're looking at is actually potentially largely automated, and then you walk out the other door on the secure side. The whole thing is done on over in within less than a minute. And the throughput of that lane, as we're seeing there, we estimate, is almost double from what you actually do with a conveyor belt system. Because if something has a problem in the thing, everything else keeps moving, but in the conveyor belt system, everything stops. And the way to do it is they have multiple conveyor belts and they shuffle people to the other conveyor belts in order to actually keep it through. But that's sort of where we are working towards. I'm going to see if I can actually get it to work. Where's my mouse? What? So there's no audio here, but this is a demonstration of what this checkpoint of the future potentially looks like. So people walk up to their cubicle, they get in the thing, they get scanned, take the luggage out, and they walk off to the outer door. So here's another door. That door now closes, and then the door in front of this lady opens, and she steps into the cubicle, and she puts her luggage into the thing, she answers some questions, and the whole thing is get ready to get scanned. Oh, she forgot something in her pocket. Takes the luggage and she's on her way. So that's a concept demonstration. I mean, to some extent it's all smoke and mirrors here, but this is sort of how we envision that actually would go in the nearish future, probably somewhere in the next 3 years to 5 years is what we're sort of hoping for.
With those self-checking bags and to the airport, what happens? This is for people that do the right thing. What happens if people don't do the right thing? Is there any way they can smuggle things, even though? So is there any other supervision? Because I cannot put all stuff into the scanning and have them somewhere else, or someone else can hold it for me. Kind of seeing as a security risk of how you system.
You're right in that, and there's definitely several measures. I mean, first of all, it actually is the metal scanner. It actually is not a metal scanner. It actually is what we call a microwave scanner or millimeter wave scanner. So it actually is so accurate, it actually can tell you have something in your pocket, or something in your hip pocket, or something in your, or that you have a chain around your neck. It actually will be able to tell that sort of things. So that's one part of it. The second part of that, in that whole cubicle thing that we actually seen, there's actually video monitoring. So the plan is that some of this video monitoring will actually automatically recognize that, oh, this person left something on the floor, or things like that, or she left something else somewhere else. So first of all, anything that's on your body will already be picked up to some extent. If you left something on the floor, it actually will be picked up. And even though it actually is self-service, there's still somebody potentially looking at the screen somewhere else.
So there's no potential contact with the third person, so that's going to be in an isolated area?
Sorry?
Because, so if I go through that checkup,
Yeah.
I might have another person with me, or is that going to be already isolated from the actual,
Yes.
so the public?
Yes. It's aimed. Yes. It is aimed for single person only. And yes, there is a recognition that some people may need help, or some people traveling with children. And then in this whole lane, the one that we saw in the beginning, this one, the typical setup would be that there would be something like 7 of these units that actually are for single person use only. And there would be an 8th one that actually is a bit more open, and people that actually need some assistance, either because they're in a wheelchair, or they have something else, or they have children, or they need some other level of assistance, they actually get directed to the one where there's actually somebody there to actually help them. So that's the current thinking.
Well, I can see a lot of issues implementing application-wise, so there's going to be, so that's, thank you.
Okay. So this is sort of like what the whole thing looks like on the inside. So at the top is sort of this concept model where you actually have this baggage scanner and these 2 panels, which is the millimeter wave scanners. When we take that machine and we give you an exploded view, there's a lot of things going on here. In the center is the bin. So this bin is actually quite large. We sort of, at some point, we sort of were actually a little smaller, but eventually somebody sort of said, oh, if it actually is this size, it means I actually can get 2 roller bags in it. or I can actually get a roller bag and a children pushchair into it. Or so we figured that out sort of like from a first class passenger that comes up with 2 roller bags, or a computer bag and another bag, and so everything will pretty much fit in there. So we believe that virtually everything will actually fit in this bin. It's actually 60 centimeters wide and by 80 centimeters high, so it's actually a fair volume. Then on the side of that bin, the white panel, is then the actual X-ray detector, which is actually the one that we actually have is a first off prototype from another company. It's a 40 by 80 centimeters flat panel X-ray detector, which is huge. And we're using that. And then with that, in this system, it's not very visible, but there's 6 X-ray tubes, 3 on this side and then 3 on the other side, that all work together to actually take a view through the bin onto the detector, and to make sure that we cover every aspect of the bin, and then we rotate this bin around. So instead of having a conveyor belt and rotating the X-ray tubes, we actually have the X-ray tube static, and we rotate the luggage in this thing. So slightly different concept, but altogether, because we're using 6 X-ray tubes, we can place them a lot closer to the whole thing, and because we divvy up the picture taking between these 6, we can still cover the whole bin with a level of resolution, is that we can actually get down to 1 millimeter cubed inside the bin in terms of what actually is in there. And we're also doing a thing where we're actually using X-ray with 2 different energy levels. This is getting a bit technical, but it actually allows us to actually work out what the atomic number is of the part, the little cube millimeter, inside the X-ray, inside the luggage. So we know if you have water or you have normal Coke or Diet Coke, we actually can see the difference between these materials. And obviously the aim for that is to actually look for highly organic materials that potentially could be explosives. Obviously that's what we're sort of looking for. And then with the whole thing is that, so there's the X-ray tubes, and there's the bin, and there's the detector, and then we have all these covers, and all these covers are completely lead lined, and the door needs to move, and that's one of those interesting things where we says, holy dooly, this door is about 100 kilos. How are we going to move this in a way where it's actually safe without cutting somebody's fingers off? And so there's all these interesting little challenges, and in the end we actually found a controller that actually is designed to actually handle elevator doors. So this actually using the same motor drive and the controller as is used in elevator doors, which actually have string and safety requirements of if you stick your hand in the elevator door, it actually won't snap your finger off, it actually only presses with a maximum of 150 newtons. And that's it. And then it says, oh, something in there, and it actually opens up again. Works beautifully. So.
Are all explosives organic materials?
That I don't know.
What's a battery?
That I don't know. There is a certain level by which we can detect this, and now we're approaching a level of secrecy that I'm not entitled to know. We're developing this thing for the TSA as a prototype. So the aim is that this unit will go over to the US, and they will use it in a 6-month cycle of actually rigorously testing to see if it really does what we claim it actually will do, but also to qualify it against what they understand as being explosive materials, and to see at what level we can distinguish them. But that is a level of information that we're not being told. All we need to provide is a mechanism whereby the system can say, oh, if it's this atomic number and this atomic number, then you need to flag it as something else, and they kind of provide that information right there and then in their secret lab, because we're not told. And so it's another interesting thing. We just need to provide a mechanism to do it. So. Yes?
My company is that I had trouble with that, having to bend down to pick up something off the floor. I've got a bad back.
Yes?
I like to think of that. And
There's a button on the screen that says, I need help.
That's not the idea, is it? So, that leads to the suggestion that you might need to have some sort of height adjustment. So that something put a bag in this height or the other thing,
Yes.
and then it will level back at that height. And it occurs to me, if you do that, if the floor drops, you don't need a sliding door. What do you think about it?
Yeah, I think we have thought about it to some extent. We actually had a variant of this system that actually had the level where to put the luggage in, essentially on hip height, sort of like what you're saying, where the door, instead of sliding door like this, the door is actually sliding down to the bottom. But the general case is that people come with roller bags, and they're already on the floor, and the closer this is to the floor, generally speaking, is what we found as being the preference. We are even going to the point of where we're actually building this into this checkpoint system here. We're actually going to lift this floor further up. Partly because we need to put detectors inside the floor, but also partly to actually get the whole bin and the opening from the door even closer to the floor, so you don't have to lift your luggage very much. No. Yes. Yeah. Yeah. Yeah.
So it seems to me that's leading towards the fact that there are two classes of luggage.
You're absolutely right, and you're really touching on a point that actually requires quite a bit of study. We're not doing this thing all by ourselves. We're actually working with Monash University. Monash University actually doing a lot of study around the whole motion and what we call the sysops, or like how does actually work with people and how many variations of people there would be, and how we deal with these sort of things. So we're working through the problems in that sense. And yes, in the end, it comes down to, says, I'm not really handy with this luggage, can you help me? And then yes, you go to item number 8, because there's actually somebody there that actually can help you. So, yeah. Yeah.
With the ramp and the issue of getting luggage into the compartment,
Yeah.
would you not be able to use a mechanism similar to what we would use for CDs and DVDs to just have something that pulls it in?
It's on a tray.
Sorry?
You put it on a tray and the tray goes in.
Well, you could, because you're already elevating the floor, so you could build something into the floor that you could pull inside the compartment.
Yeah. Interesting thought. Interesting thought. I'll keep that in mind. We haven't thought of that. I mean, part of the big problem is that all these little shields that you have are all lead lined, and also there's a thing in X-ray equipment where we talk what we call labyrinthing, which means if you have two slides like this, it doesn't work. In the sense, like you actually need to have a corner here and you actually need to have a corner here in order to actually allow the area where the X-ray bounces around to actually allow it to bounce around as much as you can. So doors will have to slide into your V shape and things like that. And but there's a whole bunch of trickery going on to actually make sure that we actually don't expose any X-rays to the outside. So not easy. So we're still expecting quite a bit of issues by the time we're putting this together. Because all this is very new. We currently are in the prototype phase. We had to get some of these panels and that sort of things, and this is sort of this metal on the corner is sort of like this the blank steel unpainted version. And there's a lot of detailing still going on in actually the mechanics of this to actually make it properly work, and including applying the shielding and the lead, because there's like currently we're estimating that there's about 2.5 millimeter lead across the whole panel, which is a fair weight. This thing becomes an issue in terms of manhandling and not crushing somebody. So
Faraday cage can't shield it enough?
Faraday's cage is electrical. It's not necessarily sort of, but in a lot of ways the same principle applies. But like in Faraday cages, if you actually have the openings in Faraday cages close enough for the frequency that you're trying to do, You basically, you can have a door and you can actually have kind of fingers rubbing on the edge, and then, but you can have an opening underneath. For X-ray, that opening underneath will go straight through. So you really need to have then a door pull on the other end that actually folds over, and then the door closes like this. So you actually get enough bouncy ways for the X-ray to actually to bounce around, because every time it bounces, it loses energy to the point where it finally comes out, it loses enough energy so it's no longer a problem. That's sort of the trick. But with moving doors, that actually is all very tricky. Okay, now we're getting really technical. This is sort of a picture on what we call this system architecture, on what's all going on in this thing. So just to point out a couple of things is that in the center here, in this thing, is basically the system computer, which is essentially just a PC. It's an embedded PC, but it's just a PC. That actually is what we call the director of everything. It doesn't do anything very special other than make sure that everything happens in sync. It's basically the director of the orchestra. Then in the blue part is the luggage handling. So we need to operate doors, and we need to operate two doors actually. So there's a front door and a back door. They operate independently. And also this bin needs to obviously rotate. So there's actually stepper motors and all sort of things, and they actually need to run at constant speed, all those sort of things. And then we get to this big yellow block, which is what we call the X-ray generation thing. And that's where it actually gets tricky. So we have 6 X-ray tubes, and they actually has signaling to be turned on and off. But all that wiring sits at minus 160,000 volts. So the solution we thought of was this, is that that's sort of a bit demonstrated in this sample. So this is sort of a sample of this tower, and the X-ray tubes is bolted onto the outside here. But inside here, we essentially just have copper piping. And the copper piping is the one that actually holds the 160,000 volts. And then inside this piping, we actually run wires. So we run these wires that we're describing here up and down this pipe to actually go to each and every tube. And that actually sits at 100 minus 62,000 volts. So that's a bit of a challenge. But then the next thing is that now we're talking about CT images. It means we actually take a lot of images, and the plan is we take 360 images when the bin spins around. We take 360 images, and we need to synchronize that all in such a way that when the bin rotates, there's a signal coming from the bin in terms of it tells me exactly where I am every time, and then on the tube side it says, okay, when you hit position 375, I'm going to fire tube number 1. And then that happens for something milliseconds, and then we need to trigger the detector that actually sits on the other side, that actually grabs the image and actually shifts it into the imaging computer to collect. So we're collecting in 12 seconds, we're collecting 360 images that all need to be processed, and they're all fairly big pictures. So that computer on the side is what we call the imaging computer. That actually is a fairly hefty beast. That actually is a large industrial rack style computer with 2 probably top of the line GPU cards in it in order to process this, because what we don't want takes 12 seconds taking 360 images and then set a minute for it to actually process it all. Now it needs to be done in 2 seconds. So there's a bit of a challenge actually to synchronize all that. And then the system computer on the other side is sort of then actually has some displays, and there is some special checking for making sure that everything is in place. Is the door closed? Is the bin operating at the right speed? And all these safety checks before we are able to actually activate the high voltage, because there's all these requirements actually we need to meet. Even down to the point of we need to turn on a little light that actually says X-rays are on. That says the requirements. We need to do this. And then if the X-ray light fails, we actually need to stop. So we had to build, I mean, it used to be when you actually had filament level light bulbs, then there's a little filament that actually creates a circuit that actually enables the X-rays. If the light fails, then the X-ray stops. We no longer have these things. Nowadays we have LED lights, so we actually need to do special things to work out if the LED light is working, which is tricky in itself again. So, as you can see, there's a lot going on in a system like this.
Can you just measure the current of the LED, and if it stops working, there's no current flow?
That's essentially the plan. That we're measuring the amount of current, and then the current needs to be within a certain window.
Yeah.
So if it's too low, something is wrong. If it's too high, something is wrong. Because sometimes you let go open circuit, sometimes you let go short circuit, and then we need to find that window to actually say that it's on. You're exactly right. This is what we're doing. So, again, you're getting a bit. I mean, if you're starting to fall asleep now, you need to tell me. But this is sort of the thing of the details that actually go on how we're actually activating these tubes. And so, at the top in the green box, this is where the high voltage comes out. This is the box. This is a Spellman, which is a third-party supplier that actually makes these things, 160,000 volts. Because for this prototype, we didn't want to develop our own yet, so we're actually using a third party for this one. And then there's the tube themselves, and there actually is some electronics within the tube itself that actually where we can tell the tube to turn on and off. That wiring goes through that tube that we talked about, and then it actually comes out to a little device which actually is an optical isolator. So optical isolators are to isolate electrical signals from one end to the other, and there's no electrical connection other than a bit of beam of light between them. Problem is, off-the-shelf optocouplers are typically 4 kilovolts, something like that. Now we need to have something which is 160,000 volts, and we're designing a custom version of that. And the first one we were actually testing yesterday, and it failed. Because we had lighting rods that actually were 50 millimeters long, and we actually had lightning sort of go past the rods all the way to the outside. And so we're now back to square one and need to figure out a way of actually making sure that it doesn't come. Either making longer rods or changing the way the epoxy, because part of the thing is the potting problem again, where sometimes the potting doesn't adhere to certain materials, and that could be a problem where we actually probably have an air gap coming along these rods and failing it. So there's all these little tribulations on that one. So that's the optical interface, and then down the bottom we have some custom electronics where we're doing this thing. The key thing is it's measuring how much current comes from the tube, and then we're actually running it through a regulator to actually tell the tube itself how much current it actually is supposed to do. And also, because there are multiple tubes, we need to send signaling down this optical pipe. It's like which tube is supposed to be on and off. So that's sort of roughly what the architecture is. And the next thing is then, okay, well, I mean, now we sort of got electrically, we got this sort of roughly right, and we understand that we actually have 6 tubes and how we need to connect them. Now we need to, how mechanically need to put them together. So, in this picture, this is the same picture we've seen before. 6 tubes on a metal style pipe with openings on the side similar to that, but then about 1 meter high. And it will actually have 8 openings. 6 tubes plus something else for the optical interface and something else for what we call the bias generator. And so there's a lot of high voltage interfacing there, and we found the most likely way to succeed with that is by doing it in 3 segments. So in the middle picture we actually have a top segment, we have a middle segment, and we have a bottom segment, because that will actually fit in our potting machine, and that's the volume of potting we actually can handle correctly at that time. But that potting is quite heavy. I mean, I would invite you to actually come and actually have a lift of this. This whole tower weighs by itself, without anything on it, well over 60 kilos. And again, other than the LED shielding that we have to put on the outside, that is also a major part of the weight of this machine. And the picture on the far right is a little bit of what we talked about before. So the one on the top is which is optical interface that we were talking about.
So I apologise for walking out.
That's all right.
Nothing to do
You're very welcome. Thank you. So this is the picture again where we talked about. So this is the piping that we're talking about, where these wires actually go through. This is this optical interface thing. These are these rods of the light pipes that actually need to come thing that we just had a problem with, and we actually now need to rework and redesign to actually work out this thing. All this, remember how we talked about these little spiky things at the beginning, where the electric fields, or how we actually want spiky things in order to get the electrons out? Here, we actually want the opposite. So that's why we have all these shapes, there are all these round shapes in order to smooth out the electric field in order to make sure that nothing arcs over instead of. So we want to keep the electrons in, not come out. And we're doing the same thing here. And here we're actually having this stack of circuit boards. This is part of generating the high voltage side of things. More pictures of the same thing. Again, this is the tube. This is this tube that we sort of have here. This is a pipe. This is some electronics that sits inside. This is what then we call the cathode controller. So that's the piece of electronics that actually regulates the current through the tube. It needs to be sitting close to the tube. And more examples of the same pipe. This is the same pipe that we actually have there, but normally it would be in metal. And we have various forms that we tried it, and then we actually cut it open to actually make sure that it actually is without any voids and with any holes in it. And we had various levels of success there sometimes, where we actually said, oh, okay, we didn't expect this. Or where it actually shrunk, or it actually came loose from the pipe again, and things like that. So again, it's come back to this testing and learning thing. It's all very experimental. Some examples of where things go wrong. When you mentioned how I sort of said the potting sort of sometimes didn't adhere to some other materials. This picture in the middle there is an example of that, where we had a stack of PCBs and they need to be mechanically bolted together in order to actually stack them up. And then the voltage actually goes, and it followed exactly the distance between that one material and the other material, and it actually worked its way through and failed. And at the bottom you sort of see something where, sometimes this happens, where this top surface interface was not flat enough, and we didn't have enough pressure on the washer, the silicon washer that was between. And this is then this little screw that I talked about before that we specifically made out of the potting material itself, because it then would have the same chemistry, it would bond properly, it will have the same thermal expansion things as the rest of the potting material, and then we found that this works. It's expensive to make. It's 50. These are machined from solid epoxy. There is indeed, there's a project going on where we're actually looking at other ways of actually doing this, either injection molding them or, but the problem is a little bit is potting material. It's not like a plastic thing where you injection mold it and you just squirt it in with high pressure. So there's different ways that we're actually trying to work out what it is, either halfway and then we only have to sort of do the shredding thorn or something like that. We also found issues where even when we're doing out of potting material is that how long the potting actually has cured. Like if you actually take potting material, because we're actually potting pipes over rods in order to machine this out of. If we actually have potting that actually is like 48 hours old, that's the perfect one. If you leave it for a week, it actually cures further and actually becomes so brittle and actually falls apart in the machine.
Right, so you've got like a nice window.
Yes, exactly, exactly. So there's a bit of a window there to make that happen. And this is part of the generator we saw before, and that picture there is actually this thing here. Oh, I lost it now. Where am I? Okay. And then we got to the end, and this is the end result that we're looking for. after all that and all that experimenting, this is sort of what's happening. So when you take 360 images, then there's a whole bunch of algorithms going on to actually 3D reconstruct the 3D image. You actually can get a bag out of this, and you can see everything that's in the bag. In this particular case, it actually is shown where the denser materials are typically metals are actually displayed in blue. So you actually see the wheels of the cart or the screws or the part of the zippers and things like that. Some of the organic materials are sort of then indicated orange, and you see the sort of the bottom of the shoes, which is rubber, typically in this particular case. You see a hairbrush, so you actually can see all the items inside the bag. The aim now is that in first instance, most likely there will be somebody looking on the screen and actually saying, yes, this is good or not. The aim for this is that we eventually will go to machine vision applications where the computer actually looks for things in this bag that actually are not correct. And we can do two things. We can either look at the straight images as the 2D images, where we actually can look at shapes for guns and knives or anything that we actually think for. And in the 3D part, we actually can look at the amount of volume of a particular type of material and actually says, oh, there's a whole blob here that actually is actually of material that we don't really like, so something going on here. And then we actually alarm it, and then it actually goes. That's where the future would go. That whole automatic checking, probably a while off. First, we actually need to produce a machine that can create these images. And that's what we're currently aiming for, to deliver this to DHS this year. So that was the end of it. I hope it was. So I brought some things. Come on and have a look if you want. And
Where does all the money come from for this development? Grants?
no, this is not a grant. This is, yes, there's a combination of things going on. This is developed under contract with DHS in the United States. So we actually have a contract with the Department of Homeland Security to build and deliver this. And as part of this contract, we're building two. So this is the first one, and then we're building in 3 months, we're building the second one that they actually can use for validating this. So the Department of Homeland Security in the United States is actually investing in this sort of things because they see opportunities for this to actually change the whole way security scanning in airports works. And I think I mentioned before, if you look at the budget for the TSA, the security scanning people in airports, half of that budget is just labor cost. So from that perspective, they're interested in actually investing in these sort of things, in this sort of technologies, to actually see where it goes, to look for opportunities where they actually can, A, make it better, make it more self-service, so they actually can use less labor to make this all work. So by and large, and at the same time, because we're actually putting technology, we're developing technology for our own company as all those sort of things, some of the funding actually comes from our own investors as part of our development. So even though we're selling products, currently we're actually a pit of money. So yes, we're making money from some of the products, but by and large, it actually doesn't cover any of our expenses. So,
just going back to the X-ray machines.
yes.
How else did you get them into hospitals when you demonstrate all these potential problems and ability for the high voltage to come out of the system?
All this equipment is qualified and tested, obviously, before. There is, in terms of the safety for the high voltage, there is a lot of stuff built in whereby it immediately stops operating if something goes wrong. And for taking X-rays, for instance, is that there needs to be a qualified radiologist actually to operate these things, and that actually is what's legally required to do these things. I mean, I actually had to go through a course. I'm actually illegally a radiologist, but I'm not allowed to do living tissue as part of this thing to operate these sort of machinery. And there's all sort of things like when they're taking a picture, they step away from the thing to actually minimize the exposure that they get themselves, and they push the button. But there's a whole bunch of electronics around that button that if the button is pressed too long, it automatically stops. If you release the button too soon, it immediately stops. And there's all these sort of mechanisms to actually to build in this level of safety, and that's all of that is actually required by standards to actually to help.
You had to have all that together.
Yes, you had to have all that. The same thing with this baggage scanning thing. I mean, is that there's a whole bunch of things, and I think I mentioned to somebody, is that there's some weird language in some of the standards where they say if the door opens, you actually need to mechanically or physically remove a piece of wire from the circuit to power it off. And so even if you have a super duper safety standard, industrial safety standard switch, that's not good enough. You actually need to have a switch that actually, and we found one, that actually is a little metallic bridge that actually pushes into something to actually make the contact, and when it's removed, you physically remove part of the circuit in order to meet the requirements. So, and the same thing with these X-ray lights we talked about before, is that if the X-ray light doesn't work, or actually has the wrong amount of current, you need to switch off. And there's all sort of things that we need to do to make that work. Double switches on the doors, X-ray lights need to be on, all sort of other validations need to be happening. So when something goes wrong in our software, the hardware actually stops it automatically, says, oh, things take too long, so stop. All that sort of things.
How would you know that the epoxy didn't set right, and over a period of time that grows?
What we do is we test it under high voltage. It's sort of like once we sort of we potted it, we actually test it to the maximum voltage that it needs to be plus 10%. And then we put it on the high voltage and we actually leave it sitting there for 24 hours. So, and at the same time we do all these quality and procedure checks. Actually, is the potting mix that went in, was that right? What was the temperature? What was the humidity? So we check all these parameters of the process to make sure that we're actually doing it right. But then we test it. Yeah.
So do you have, assuming this all works and you've got a nice product at the end of it, do you have plans to do the volume manufacture yourselves?
Yes.
Yeah?
Yes. We definitely have plans to do the volume manufacture itself, although for this particular product, this baggage scanning thing, we think the initial first big market will be the United States themselves. So the thinking is that we would do the X-ray tube down here in Adelaide, maybe do the generator down here in Adelaide, but the actual MBS system itself is likely then to be manufactured in the US. Yeah. By the way, because I mean, there's all sort of interesting things, or like we're planning to ship this thing, but we're already sort of talking to exporters and that sort of things about the paperwork required around X-ray equipment, and just phenomenal. To the point where we're actually thinking that rather than actually sending the whole assembled machine, that we're actually planning to actually send the tubes by itself, separately. So the machine itself doesn't have to be declared as an X-ray machine. Oh, this is just a machine. And then whilst we're in the US, then we actually add the X-ray to it. All that sort of funny tricks. But
and you guys have the capacity and space at Tonsley to scale up for that?
We have the capacity in Tonsley to scale up the tube manufacture, but we don't currently have the capacity to build these sort of machines.
They're big machines.
Yeah, they're really big machines and they're really heavy. And really, because these panels are so heavy by themselves, they need manhandling. On that same level, we're already thinking about the future, because we're now building these machines, and you really think we're already thinking about the next step on this sort of thing. Is one of the things we're talking about now already is to actually split these panels. So instead of one big panel, actually split the part with the door and split the part with the screen on it, and then split another part so they actually can come off separately. That would actually allow serviceability a lot better. But at some point, given the complexity of this thing, you'd go down a particular path, and then that's where you're stuck with it, and you can't really change it now at this stage. But for a future product, we plan to do that.
What's the advantage of using X-ray instead of laser technology for this, especially for the airport?
Well, X-ray penetrates, laser doesn't penetrate.
Oh, well, actually, in mining, I was involved in projects where the laser actually penetrates and it's able to detect and actually do 3D on a computer version of what it actually scans. So that's being used mostly in the mining industry, but I could see the application here. So that's where I'm kind of thinking what the advantages are of X-ray that laser can do, but you might not be aware of
I'm not familiar enough with laser to actually give you a straight answer whether they can. My experience is.
Curious to know what wavelengths he's working about. I mean, terahertz, maybe you get some good penetration from materials, but I mean, these things are just opaque to anything optical or infrared.
Yeah, so the laser that I'm talking about, so usually in mining industry they use that to scan the entire, so in searching for resources, they have to scan the actual earth to see if there's enough, so they don't dig anymore until they actually have the proof of saying that there is enough of resources to start mining. And I've seen it in action that it actually, in terms of not even like a mining nowhere, but let's say this house or this building, it had the capability to scan it and it would detect us if we should give you a full 3D picture on that one. So don't know if that's the laser itself, but there's a software company that kind of does the other bit of the actual visual, if you know what I mean. So laser itself might not have that capability, but there might be a software that can do that with laser. So looking in the future, because you're talking about developing, this is going to be massive. And as soon as you're enter, you're going to have other people coming up with other technologies as well. So
Yeah, I mean, just this week I was in a talk where they were talking about using optical scanning for body functions. So, I mean, like your sort of your sport watches actually can actually measure your heart rate and things like that by using an optical thing. They want to take that further, and there's some studies being done where they're taking that further, but they can. The interesting thing is that they actually can get down to an accuracy level which is actually astonishing, to the point where they actually can measure blood flow by the actual blood cells that are actually moving along. But the penetration they actually can do is about 2 millimeters, 2 millimeters deep. And the only other option they have in order to get deeper is actually put the whole thing in a needle and actually poke you with it and actually poke around with the needle to actually get to that level of information of what's going on.
So they do it with just hanging out the land as well. You dig core holes and you put laser systems down, and it's just measuring the inside of that.
Essentially the surface area of that borehole. Yeah.
And then, you can stitch all that data together and get some kind of idea of what's in between them.
Yeah.
But it just doesn't
Yeah.
Yeah. But again, you're in this regime. Yeah.
Cool.
Mark, sorry. Are you guys doing R&D on the creation of the cold cathode itself? You mentioned that it's essentially quite random. Is there any efforts to try and increase the efficiency of how many emitters you have, how many useful emitters you have per square centimeter or whatever?
I don't know that particular answer, but there is definitely things going on in terms of changing the recipe. Part of the problem is also trying to work out what your current density is per square millimeter. And there's a lot going on in terms of the tubes, because one of the things with X-ray tubes to some extent is that you're creating this cloud of electrons, and you actually want to hit them on the anode within a millimeter, because that becomes your focal spot. And that actually determines how accurately you actually can take images. So there's a lot of things going on the shape of that emitter and how you actually can control the focus of this thing. So there's a lot of research happening on that level. And there's issues around, okay, well, here we have an X-ray tube, like one version of this one X-ray tube that we have here is designed for 160 kV, but only at 1 milliamp. For this MBS system, we actually want to run it at 7.5 milliamps. So there's a bit of R&D going on, says, well, what is size of the emitter do we actually need in terms of surface area to last 7.5 milliamps? And when this system runs, and it runs for 3 months, 24-hour operation, we have taken 5 million shots on an X-ray tube, which is just astonishing. And when you sort of calculate that out, and people say, really? That many? Because I mean, the normal tube that we actually have in the cart is doing a couple of hundred shots a day maximum. And then with 1 million shots, it lasts for its lifetime. Now we actually potentially need to change these X-ray tubes after 3 months, because they don't last those 5 million shots. Part of the suggestions that is happening is that when you're doing this quick pulsing on these tubes, is that those little nano fingers that actually point up. Part of the things that happen in this nanoparticle stuff is that they are not always equal height, which means the ones that are the highest actually conduct more current than the other ones next to it. And then they burn off. And then the next one actually comes in. So part of the conditioning of the tube is what we're talking about, is actually, I mean, in a crude way, burning off the peaks. So everything is actually as equal and smooth as possible. And another suggestion to some extent is that when we're turning these tubes on and off, is that some of these particles may actually move to the point where they actually may break off. There's a whole bunch of R&D going on of things that we don't know in that area yet. So at the moment, we're actually not sure that these tubes can last for 5 million shots.
Well, that's okay, because then you still the consumer.
Yeah. Oh, we just making more tubes, right?
Okay, let's put our hands together again for Martha.